Section 22.4, Faraday's law of electromagnetic induction. So I've alluded to Faraday's law, and it has to do with our magnetic flux. Faraday's law states that the average EMF that's induced in some coil has n loops, right, n wraparounds. You can calculate that EMF with negative n times the final magnetic flux minus the initial magnetic flux divided by the final time minus the initial time. Or more compactly, you can write it as the EMF is equal to negative times the number of loops n times the change in magnetic flux divided by the change in time. This is a really powerful statement, and you'll notice it's very similar to what we calculated or what we derived in the motional EMF section. This is just a more general expression. It includes if we have more than one loop as opposed to just a single loop around. And the negative sign also has to do with the direction of that induced EMF, which is something we'll see even more of as we continue. Now, what is our SI unit of this induced EMF? The SI unit is the same as that of potential or a voltage. It is the unit of the volt, capital V. So that's nice. It is very consistent. Let's see how this law plays out in an example. Example 5, the EMF induced by a changing magnetic field. A coil of wire consists of 20 turns or loops, each of which has an area of 0.0015 square meters. The magnetic field is perpendicular to the surface. Initially, the magnitude of the magnetic field is 0.050 Tesla and 0.1 seconds. Later, it has increased to 0.060 Tesla. Find the average EMF induced in the coil during this time. Let's take a look. What is given to us here? We know we want to find the EMF that's been induced. So that's what we're looking for. And we've been given quite a bit of information. First, there's this 20 turns. Notice that's also loops. That gives us a clue that this is just our capital N. They also mention the area here of 0.0015 square meters. And then let's see other numbers. We have initially the magnetic field, and then later it has increased. So that means I'm going to call this first one B sub 0, versus the later one is just going to be capital B for the final magnetic field. We also note that there's this time, 0.10 seconds. And notice that is the difference between the initial and the final. Because we have at some initial time we have one value, and after this time interval it's increased to this other value. So I can describe this as my delta t. This is looking really good. We have a lot of the different variables accounted for here, right? If we remember, our EMF by Faraday's law is equal to negative n times the change in magnetic flux all over the change in time. And we can remember how we calculate our magnetic flux in the most general form is going to be the magnetic field times the area times cosine of the angle between those two. So I've seen n, I've seen the change in time, I've seen the final and initial magnetic fields, I've seen the area. What about this angle? Any ideas on that? Well, this one we have a clue for in the words of the text, right? Notice it says a magnetic field is perpendicular to the surface. So if we drew this, we would see magnetic field lines that are going perpendicular to the surface of the coil, right? Where if the coil has a normal that's that way, the angle between the normal and the magnetic field is going to be 0. So that's one you have to read carefully because it'd be easy to say, oh, perpendicular, 90 degrees. But you have to pay attention to what is actually perpendicular. All right, now that we've set all this up, let's take a look. So we have Faraday's law. The EMF is negative n times change in magnetic flux over change in time. And if we plug in our flux equation, we have BA cosine phi minus initial B times A times cosine of phi. Get my drawings out of the way there. There we go. And the key here is we want to pay attention when we're looking at the change in magnetic flux to what's actually changing. It's always got to be something changing in order to have an EMF that's induced. In this case, the area is constant. That's going to be the same in both of these. That's not changing. You also could have the angle changing, but the angle stays the same because the loop keeps the same orientation. What does change here is the magnetic field. Notice the magnetic field increases in value. And so that's going to be the change that we focus in on that causes an induced EMF. Since everything else is the same, we can factor it out, right? Including the cosine, that can come out too. So A cosine phi can come out in front. So we have n times A times cosine of phi times our change in magnetic field all over our change in time. And these are now all variables that we've identified. So we can plug in -20 times 0.0015 square meters times cosine of 0 degrees times 0.060 minus 0.050 Tesla divided by 0.10 seconds. If you calculate that out, you should get -3.0 times 10 to the -3rd with volts, because volts are our SI unit of the induced EMF. So this highlights some of the ideas of how we can use these equations in approaching this. Let's look at one more conceptual example. An induction stove. Two pots of water are placed on an induction stove at the same time. The stove itself is cool to the touch. The water in the ferromagnetic metal pot is boiling, while that in the glass pot is not. How can such a cool stove boil water? And why isn't the water in the glass pot boiling? This is an interesting thing to think about, right? Why is there this difference? What magic is going on here? Because it sure does seem like magic. Well, the key is that it's a ferromagnetic metal pot. We know that metals are good conductors, and it's going to connect to our electromagnetic induction that we've been learning about all chapter. So the way that an induction stove works is there is an AC coil below that's quickly changing its direction and inducing an EMF within the pot because it changes the magnetic field. That coil creates a magnetic field, like we learned about last chapter, and that magnetic field is constantly changing as the current flips direction. Since we induce an EMF in the pots, the metal one is a conductor, so it's able to create an induced current as well. And the metal has a finite resistance, so eventually it's going to start giving off that energy that as heat, right? That's what resistors do if you have enough current passing through them. They get hot. The glass, meanwhile, is a really good insulator. So even though it has an induced EMF, it's not going to have an induced current. And this is something that won't actually heat your hand up, which is why you can touch the stove, which is pretty nifty. So if you get a chance to see it, check out an induction stove, you'll be able to explain why it works and just be like, aha, Faraday's law of electromagnetic induction. It all makes sense.